Hello everyone, this is Monica Lupion, your instructor in the course Heat and Mass Transfer. Today I'm gonna solve a problem that we discussed in the lecture dedicated to unsteady state diffusion, which is part of mass transfer. So just to refresh in memory, when we discuss unsteady state diffusion, we found out that the general equation for unsteady state diffusion, that is when there is dependence with time, is that the D concentration over time is equal to the diffusion coefficient times the differential equation of the concentration with the position. And I mentioned that we can follow two main strategies here. One is to directly solve this differential equation using analytical solution, using mathematical skills and tools, but it's not easy. Depending on the geometry, this could be quite a challenge. And actually, even with relatively simple geometries, like in the case of this plane that is indicated in the slide, even if the geometry is relatively easy, the solution can be quite sophisticated, as you can see. It's a series. And again, it's not very easy to get to that solution and to apply that solution. So the second alternative, which is much more practical, but of course it has some limitations as well, is the utilization of the concentration time charts for different geometries. You got all these charts that we call high-select charts in the appendix F. So depending on the geometry, you will see a chart for the case of a plane, a cylinder, and a sphere. Okay, and these appendix F, the concentration time charts that we're going to use for mass transfer are exactly the same as the ones that we use in heat transfer. Just the parameters, the Y and the X parameters will be different, but we should be able to use exactly the same graphs. Just, of course, taking into consideration that the parameters that we're going to use are going to be defined in a different way if we consider heat transfer than if we consider mass transfer. Okay, so let's go for it. Let's go for the example. So in this case, we have to consider a rectangular shape gel tablet of thickness 0.652 centimeters and width 1 centimeter, which is loaded with the drug Dramamine. The edges of the gel tablet are sealed so that the diffusion of Dramamine occurs only along the thickness of the gel tablet. So we can consider just one dimension, okay, and we can't forget about the edges. The initial concentration of Dramamine, which is the solute A, in the gel, which is B, is 64.0 milligrams per cubic centimeter, and to provide a total drug dosage of 41.7 milligrams. The concentration of the drug at the exposed surface of the tablet is maintained at 0 to provide a constant sink for mass transfer. So for mass transfer to happen, you know that we need this gradient of the concentration. So in this case, this problem is telling us that the concentration at the exposed surface can be considered to be 0. The diffusion coefficient of the drug in the gel is 3.0 times 10 minus 7 square centimeter second. What is the residual concentration of drug in the center of the tablet after 96 hours? And we need to compare the result using A, the concentration time charts, the appendix F, and B, the infinity series analytical solution. Okay, so let's go for it. Let me change the camera. Okay, so let's go now over the problem again. And I will indicate, well, first the geometry. We know that is a rectangular shape tablet, something like this. Okay, and the dimensions are 0.652 centimeters thickness, and this other dimension is 1.0 centimeter. And we know, well, the drug is the element A, and the gel is the element B. Okay, we know that the initial concentration, COCA0, is equal to 64.0 milligrams cubic centimeter, that we can consider that the concentration outside this tablet, the concentration of the drug, the concentration A infinity is equal to 0. We also know the diffusion coefficient is given, and this is equal to 3.0 times 10 minus 7 square centimeter second. And we need to determine the value of the concentration after a certain amount of time, and this is 96 hours. And we need to determine this concentration using two different strategies. One is the concentration time chart, and the second one is the analytical solution. So let's begin with the easiest one, the concentration time chart. In the appendix F in your textbook. And since this is a rectangular shaped tablet, because of the geometry, we're gonna be using figure F1 in your appendix. Okay. So if you remember when we discussed heat transfer, I mentioned that in these appendixes, the figures, there is always a kind of a diagram in one of the corners indicating which is the element X and the element X1 that we need to use. In this particular case, if you take a look to the figure F1, you will see that this is an element like this. It's a diagram like this. And the thickness should be 2x1, and x1 is defined as the distance between the center and the surface. And therefore, x is here defined as the distance from the center to the particular position that we need to determine the concentration after a certain amount of time. So x1 is half of the thickness. In this case, fx1 will be equal to 0.652 centimeters, which is the thickness over 2. This is equal to 0.326 centimeters. Okay, so now we have a clear value of the element x1 that we're going to need to define the different parameters that we're going to use in the concentration time charts. If you remember, we have to define x, y, m, and n. We need to define 3 of them and then use the appendix F to calculate the first one. Okay. In this case, we have all the information to calculate the parameter x, and x in the case of mass transfer is defined as the diffusion coefficient times time divided by x1 squared. So let's calculate x. So the diffusion coefficient, and don't forget to use the proper units, right? 3.0 times 10 minus 7 square centimeters per second times 96 hours that we need to convert into seconds. Again, very important to do not forget the units, okay? And this is divided by x1, which is 0.326 square centimeters. X doesn't have any dimension. That's why you need to make sure that all the units are consistent. So you do the calculations here, and this is equal to 0.976. Okay. Another parameter, n, which is the relative position. N is defined as x divided by x1. And now we need to read again the problem. We need to evaluate the concentration of the drug in the center. Okay, so here in the center. And if we consider the definition of the diagram here, if we are evaluating the concentration in the center, that means that x is equal to 0 because it's the center. Okay, therefore n will be equal to 0. The next parameter will be m, and m is defined by the diffusion coefficient over the convective mass transfer coefficient Kc times x1. Now, this is the convective mass transfer coefficient. Okay, so if we don't have enough information to calculate this convective mass transfer coefficient, we can assume that the impact of this parameter won't be very significant, and therefore we can assume that this is equal to 0. So this is an assumption. Okay, so now let me get back to the different parameters that we have. We have calculated x, n, and m. So if you go to the appendix F1, let me show you. Okay. So this is the appendix F1, and we know that the value of m is equal to 0. So we have to pay attention to this area here with m, where m is equal to 0. N is equal to 0 as well. So we have that m is equal to 0, so we're in this region here, and n is equal to 0. So we pay a closer attention, and this is the line, the one that it gets in the exterior of this group of lines. Okay, so this is the line. And now we know as well that x is 0.976, so very, very close to 1. So we trace a line, and the intersection with this other line will give you the value of y. So y will be around 0.12, something like that, okay? You don't have to be very, very, very specific. So when we go to figure F1, y is approximately equal to 0.12. We know that y, the definition of y, is equal to the concentration infinity minus concentration with time, which is what we're looking for, over the concentration infinity minus the initial concentration. Concentration infinity, if you remember, we know that is equal to 0, right? It's given in the problem. So we cancel this, and therefore from here we can say that the concentration that we're looking for is equal to y times the initial concentration. And let me see, this is equal to 7.7 milligrams of A cubic centimeters. Okay, so this is the solution if we apply the concentration time charge. Now, the problem also asks what happens if we calculate the same thing, the concentration in the center, using this series, the infinite series. It's in the section, I believe, 27.16 in your textbook. I'm gonna just copy the solution that we discussed in this section. So the concentration minus the concentration of a surface over the initial concentration minus the concentration of the surface is equal to 4 over pi, and now sum from n equal to 1 to infinity of 1 over n sin n pi set, and set is defined as L over 2 because it's the center over the thickness, okay? E minus n pi 2 over 2 is quite long, raised to 2 times xd, and xd is defined as the diffusion coefficient times t divided by x1 squared that we calculated in the previous section. So this is equal to 0.976. Just give me 1 minute to clarify the value of C and the value of L. If you take a look to the section 27.16 in your textbook, the diagram of this geometry specifically is this one. So we consider from 0 to x, so the origin is one of the sides of the tablet, and the center will be the thickness over 2, okay? Because the thickness will be equal to L, okay? That's why I substitute set by L over 2, and L is the thickness of the tablet. N is equal to 1, 3, 5, 7, etc. So as long as you like. So let's begin. So the concentration minus the concentration of the surface over the initial concentration minus the concentration over the surface. This is equal to 4 pi when n is equal to 1 sin pi L square L over 2L, which we can cancel, times E minus pi 2 square xd, plus when n, this is when n is equal to 1. When n is equal to 3, we have 4 pi times 1 over 3 sin 3 pi 2 times e minus 3 pi 2 raised to 2 times xd. And this will be for the case when n is equal to 3. And then we can continue as long as we like. The more terms that we add, the more accurate we will be in the solution. But just one thing, when we get to, when n gets larger and larger, the contribution will be less and less significant. So when you solve this, this is equal to 0.115, that will be the first term when n is equal to 1, plus the second term when n is equal to 3 is 1.66 times 10 minus 10. You see that the number here is much more smaller than when n is equal to 1, plus the third number will be 1.87 times 10 minus 27. My goodness, this is when n is equal to 5. So you can stop here, and in this case, you can see that this number is going to be very, very, very close to 0.12, which is the value that we got in the section number 1, the value of y. So you can see that, well, the concentration chart, although it's not as accurate as the analytical solution, but we are very, very, very close. Okay. Okay, I hope you understand this problem. If not, please let me know. I will be happy to answer any questions you might have. Thank you.